Thank you very much. And we'll have the second in the set of lectures and aspects of de Sitter space. So thank you, Dio.
Thank you. Thank you for giving me the opportunity to continue telling you about de Sitter space. So let me discuss the plan of the day. So yesterday we did a slide overview of certain classical features of an expanding spacetime, and every result we found, I made a hint upon what it may look like upon a slide quantization. By slide quantization, I mean considering only the quantization of the field fluctuating quantum mechanically in a fixed de Sitter background first, okay? And then hopefully by the end of the lecture, we'll think a little bit about what happens if we also allow the geometry to fluctuate a little bit due to quantum effects before beginning a more speculative discussion about fully fledged quantum effects. So I think the references that are most useful for today's discussion are the following papers. This paper over here develops the Schrödinger picture of quantum fields in a de Sitter space-time. And this paper over here emphasizes the operator algebra of de Sitter fields at late times. So these are sort of useful perspectives, different perspectives on how to think about quantum fields. And these papers over here, this is a classic by Malasena, who talked about how to calculate certain three-point functions in inflating spacetimes, doing the calculation in a beautiful way. And finally, in as much as the symmetries, we're going to revisit the symmetries of de Sitter now, but now from the perspective of Wigner. We're going to ask about the representations of these symmetries. And the classic reference for this is an old book from the 70s by Dobrev et al., who analyzed this problem, not motivated by de Sitter at the time, but rather by conformal properties of quantum field theories in general. However, they analyzed the properties of the Euclidean conformal group, okay, which is useful. It turns out to be an extremely useful reference for considerations of de Sitter spacetimes, as I'll explain. It's becoming a book that's popular amongst the bootstrap community these days, I'm happy to say. So maybe they'll secretly all end up working on this problem. Okay, so, oh, and I have the answer to Loga's homework problem. So I don't know if anyone else did it, but I did. So neutrinos have order electron volt mass. Now, there's no known bound on the lightest one, but the mass differences are of that order. And if we assume that it's of the order electron volt, they're deep, deep, deep in the regime of the principal series representation of the complex lambda we talked about yesterday, which in our universe, the scale of de Sitter is 10 to the minus 33 electron volt or something like that.
I remember correctly. I don't know. Other people will hear the discussion. I'm just quoting what Vasiliev told me yesterday. Yeah. So that's so yeah. As you say, it's about 10 to the 20 times larger than.
Yeah, 10 to. So I did my homework right. That's good. I hope you all did the same. Okay. So before I start, okay, let's write down our metric just to have a frame of reference. But before I start, are there any questions about yesterday that you didn't have an opportunity to ask? Okay. So let's quantize a field, a free field in de Sitter. And let's bear in mind for a moment what natural questions in quantum field theory might be for de Sitter. And so let's pause for a second and compare the structure we talked about yesterday to that of flat space or anti-de Sitter space as two different examples of asymptotic structures. So in flat space, the spacetime provides us rather naturally a null boundary where we can define a past asymptotic Fock space and a future asymptotic Fock space whose overlap is the S matrix effectively. And that's the kind of structure that it sort of guides us to talk about. So quantum field theory very naturally guides us in flat space, in Minkowski space, naturally suggests we calculate an S matrix where we scatter from the null past all the way to null future. It sort of gives us a perfect null slice where we have non-interacting states. And in anti-de Sitter space, we are provided not with a null slice, but rather a time-like slice, where we can consider a rather larger set of objects that are sort of localized operators that sit on this boundary and give us correlation functions as functions of positions along this sort of ADS slice. That's a natural field theory question, not the only field theory question, but a natural field theory question that we're prompted to ask just by virtue of the structure of the space itself. Now in de Sitter, the situation is a little different in that inside the space itself at any finite time there's no natural asymptotia where we can hinge some particular observable. This makes the question a little tricky because what is it that we would like to calculate when we do quantum field theory in de Sitter? Is it an S matrix that we'd like to calculate? For example, the overlap of some initial quantum state over here with some late time quantum state over here? Is it boundary correlators? If so, of what boundary? So the type of questions we're going to consider, and the reason I'm giving this introduction before that is so that you keep in mind that it's not obvious and it may be a problem that requires more thought, is the kind of problem prompted by the case where it's purely expanding and it expands for a rather late time, and we're going to consider the structure of quantum effects at the very late time slice. And the justification for that might be that if the early universe is an inflationary type, and we exit this inflationary type, the scale invariant spectrum of the photons we observe are supposed to be quantum seeded by quantum effects of a scalar during that era. And what we're really observing in scale invariance is the structure of those correlations on the late time slice. Okay? So we're gonna calculate first what I'm calling CMB type observables. And for those observables, what we're going to consider is the physics of quantum fields on this very large space-like slice at the late future. Okay? So that's the kind of object we're going to start by considering. Now, of course, this is, so in addition to being sort of, something suggested by the CMB type calculations, it's also structurally nice, mathematically nice, because as we saw yesterday, the late time features of the classical field separated into objects that transform nicely under the symmetries of the problem. So recall that the classical field at late enough times had, we called it kappa, right? Sort of two natural seeds out of which it was built. And we viewed these objects over here in the classical case as coordinates of the classical field on phase space. Okay, sort of like the position and the momentum of the field itself. And when we quantize, what we do is we promote these objects to operators that act linearly on the field theoretic Hilbert space. Now, In doing so, I would like to emphasize that our quantum field in its asymptotic region has produced for us two operators that transform nicely under the conformal symmetries. So already those of you who have anti-de Sitter in mind, again, there's sort of we have to press the brakes a little bit, in that here, if we pull the field in ADS near the time-like boundary and impose Dirichlet boundary conditions, we would end up only with one operator acting on the Hilbert space that transformed nicely under the conformal group. This we cannot do in de Sitter because it would be like imposing a future boundary condition that killed half of the phase space. And in a more important way to state this is that when it's not just that we promote the field to an operator, it comes along with its conjugate momentum, whose equal time commutation relations have to obey the Heisenberg algebra. And what that means, that's just standard quantization. I haven't done anything complicated. But what it means from the point of view of our alpha plus and alpha minus is that they themselves, though they look like operators that innocently transform under the Euclidean conformal group, they themselves satisfy a non-trivial commutation relation, okay, which is given by good. So here we have to pause because, as we said, there were two different scenarios. One was the heavy particles and one was the light particles. And so let's split the object into the two cases. So by light, I mean kappa real. Kappa real. In this case, the operator algebra that follows is this one over here with an I, because when kappa is real, these two operators become Hermitian operators under Hermitian conjugation. So recall that when kappa was real, I mentioned yesterday that these were real functions of space. The quantum analog of that statement is that these operators become Hermitian under conjugation. And so if you do the calculation, the commutation relations that follow are these over here. And when kappa becomes complex, okay, you may be able to guess that the operators alpha plus and alpha minus change in flavor. They become complex conjugates of each other under Hermitian conjugation. So in the case where kappa is complex, remember the field was real, and so alpha plus and alpha minus had to be complex conjugates of each other. And what that means at the level of the operators is that alpha dagger of x plus is equal to alpha minus hat. And now the algebra they obey is given by, we can drop the plus because it's just dagger. Alpha comma alpha dagger is equal no I, just the standard creation annihilation Heisenberg algebra, operator algebra. Okay, so here's the quantum. Okay, so now we've done something simple. We've promoted our classical field and its classical phase structure to a quantum operator, and in doing so, the two flavors we saw, one which was complex kappa, which we said in the classical limit retained its sort of particle-like nature until very late times, became a collection of creation and annihilation operators, which are basically the Fock structure of creating sort of particles on a vacuum, very much like in Minkowski space. And so again, this is a beat to the same tune of complex kappa is the limit in which these are more and more like standard particles because their Compton wavelength is far smaller. Even that of the neutrino is far smaller than the, we solved your problem, Loga, okay. than the curvature of space. However, curiously, if kappa becomes real, the reality conditions of our conformal operators at the late time boundary change from complex operators to Hermitian operators. Okay, and now acting with them, though it acts non-trivial, though they may well act non-trivially in particular quantum state, they have a different type of action than that of an alpha or an alpha dagger. Okay, so this is an important. This is the sort of perturbative quantum manifestation of our classical observation. Okay, and now we can make a few more observations, which are that now we have two operators that look like local operators on R3 at late enough times, and under the action of the conformal group, they transform as conformal primaries. And we can now, with respect to the conformal group, we can now refer to kappa as their scaling dimension on conformal weight. So we can start making contact with the standard language of conformal field theory. However, this comes with a very important exclamation mark, because you see, imagine for a moment we were doing standard Euclidean conformal field theory. If I wrote, and I told you I have two operators in my Euclidean conformal field theory that lives on R3, and I told you that they obey non-trivial commutation relations, you might be a little surprised. Because when we do Euclidean field theory and we don't Wick rotate to Lorentzian space, everything is permutation invariant. Euclidean operators tend to commute amongst themselves from the Euclidean perspective. Whereas here I'm telling you that these operators that transform nicely under the Euclidean conformal group obey something like a Heisenberg algebra. And this is another reminder that yes, we're dealing with a Euclidean conformal group, however, there are Lorentzian structures encoded in it that we mustn't forget, okay? And if we drop this and just close our eyes and call it a Euclidean field theory without further thought, we may reach incorrect conclusions, okay? So I want you to bear in mind that the Lorentzian structure stays in important ways all the way up to the future boundary. Another thing you might be confused by is that if you open the big yellow book, and I told you that the range of the scaling dimension for a scalar field with spin 0 under the SO3 subgroup of the conformal group, the range of the scaling can be 0, it can go all the way down to 0, it can be complex. You would never find these formulas in the big yellow book, because there's unitarity bounds, or what are known as unitarity bounds on the scaling dimensions of fields in conformal field theory. However, the word unitarity comes attached to a particular group, and in the case that we usually analyze in conformal field theory, the word unitarity comes attached to the Hermitian conjugation of SO3, 2 rather than SO4, 1. For example, when we do what we call radial quantization in Euclidean field theory, we have to do something unusual, which is take, for example, define the Hermitian conjugate of the generator of special conformal transformations, and that's equal to the generator of translations, k dagger equal p. Or that the bra and the cat are living on different sides of the Euclidean space. The reason we do that is because we want to mimic the hermiticity conditions of the Lorentzian theory and its unitarity. And this is why Euclidean tau goes to minus Euclidean tau. So when we do radial quantization, what we're doing is we're retaining the structure of the unitary Lorentzian SO3, 2, but using the power of Euclidean techniques in order to calculate things. De Sitter is asking us, at least at the level of field theory, in a fixed de Sitter background, it's asking us to do something slightly different. For example, k dagger is equal to k. what it's asking us to do, is asking us to ask the Wigner question of what are the unitary irreducible representations of the kinematic group at hand? Okay, so this is roughly the question that we might want to ask. And maybe in answering this question, we'll get some insight as to whether or not what we're seeing is unusual. Now, so let me make an anecdotal remark before going through the mathematical results. This is a mathematically solved problem. It was solved by Harishchandra, and later for the specific case of the de Sitter group, solved in this book. It's an important piece of mathematics. The question was prompted by Dirac because he didn't understand the representation theory of SO3,1. He asked this to his then physics grad student Harishchandra, who became a mathematician and spent his career answering the question and becoming one of the great mathematicians of all time. So it's a beautiful question. But the parenthetic remark I'd like to make is that everything I say is true in 4 dimensions, but if you considered for a moment the conformal group in d dimensions, there is one case where the group of ADS and DS are the same. And I already answered my question, and that's the case of d equals 2. So that's an interesting case that we're not going to consider here, but I'd like to mention it as an exception to the rule that for the case of SO2,1, which is equal to SO1,2, there may be an overlap in the analysis. So that's just an interesting parenthetic remark. But we're not doing DS2 here. So let me now just mention the results of SO4,1, what's known. So we can label our representations by the eigenvalue, by the spin of the SO3 subgroup and a scaling weight, okay? Well, some of you may be familiar with these words because you studied precisely because you studied SL2R in the past. However, many of these words are still true for high dimensions. Okay, so, and the quadratic Casimir, which has to be real, is given by the following product. Okay, so there's an operator, a quadratic operator that commutes with all the operators, and it has eigenvalues which are invariant for all states within the representation, and given a delta and an S, the Casimir has to be real. Now, the representations, so let me first talk about the representation theory for spin 0. The representations come in different branches. There are 3 branches of unitary reducible representations. One is known as the principal series representation. For which delta is equal to 3/2 plus I nu, where nu is any real number. Okay, so already here we're seeing a hint of the structure. Then there's something called the complementary series representation. Where delta ranges between 0 and 3. And finally, in the case of even dimensional de Sitter only, proof by Harishchandra, there is something known as the discrete series representation. So this is not a representation that exists, for example, in DS3 or DS5. But it does exist in DS4 and DS2. Okay? So these are subtleties that that are very specific to the representation theory. And for these, delta is an integer. Okay? And so you open a book in mathematics on the unitary representations of SO4, and you start reading about these things and all of the functional spaces living on the SO4, the space of functions of SO4, and what inner products they have and when can they be finite. And after a long analysis, you end up with 3 cases for both positive norms. And remarkably, they're precisely the values of kappa that appeared by considering stable free particles in de Sitter. Okay, so the Hilbert space of de Sitter, the single particle, for example, Hilbert space in de Sitter, when we act with these alpha daggers on some vacuum, assuming the vacuum is de Sitter invariant, creates for you a Hilbert space that can be split naturally into these different irreducible representations, and this is how it organizes itself. And there's a few things to note. Again, what we thought was a unitarity bound on scalar particles is no longer the case. Delta can take the way all the way down to 0, okay? Even for spin 0. The assumption that you need your scaling dimensions to constitute a discrete collection is no longer the case. You can have continua. Nu is a real number. In general, if you if you take the tensor product of 2 operators, you will produce a continuum that involves an integral over all of these continuous representations. But there are occasionally, in the even dimensional case, these peculiar discrete representations as well. And these are really somehow the surprising ones, because this is a non-compact group. So we expect there to be a continuum somehow. We expect it's like Fourier analysis. What is perhaps less intuitive, at least to me, is why there's also this discretum in even dimensions. And the condition for any non-compact Lie group is that if it has a Cartan subalgebra which is compact, the maximal compact Cartan subalgebra, then these discrete series are always present. And so this is why SO4,1 allows it, but SO3,1 does not. I'll try to give an intuitive picture a little later as to why from de Sitter this might be the case, but it's worth emphasizing. Oh, good, we'll get there. In fact, they're going to become the hero of the story in a second. So far, what I've said is true. If you tune the mass of the scalar, you're only accessing these 2, except in the massless case, which is a delicate point in between. Is it the limit of the complementary, or is it one of the discrete? But okay, so now let me talk. Oh, sorry, yeah. This is for, this is a good question. Delta is between 0 and 3 for spin 0. Yeah, therefore, yeah, for spin 0, I think delta has to be an integer greater than 3 or less than 0. Yeah. If not, it's in the complementary. And for spin not 0,
the light figure gave you a spectrum from 0 to 3 by 2.
They gave, well, there was kappa plus and kappa minus. So kappa plus went from 0 to 3 over 2, and sorry, kappa minus went from 0 to 3 over 2, and kappa plus went from 3 over 2 to 3. So if we act with different pieces, we could create these different parts. Now, I should say, in both these cases, we can split the delta into what's known as a weight and a shadow, what people in the CFT literature would call a shadow weight. The shadow weight is the dimension of the Euclidean space minus the original weight. And in fact, these representations are sort of equivalent. So the representation of a weight and its shadow are equivalent. They have sort of they have the same character. Okay, and so really once you understand the weights for delta, you've also understood them for the shadow. Here, for example, the shadow weight is the complex conjugate. Okay, and so the structures are really governed by the shadow, which is from 0 to 3/2, and so it reduces the range a little bit of what you need to understand. So I ended it here because for the discrete series, there are additional conditions that occur. There's certain, which in de Sitter are gauge invariances that remove these unusual negative weights. So actually, even in the negative integer discrete series, the character is only a sum over positive integers. So it's useful to think about this case really in terms of the positive integers. It's, but I'll get there, because the story of gauge particles, the story of massless particles in de Sitter is the story in DS4 is the story of discrete series. Now, if you want to get some more intuition about this problem, I suggest the following exercise, just to get a feel of this Hilbert space in a slightly more mundane scenario. Take a particle, a quantum particle, and constrain its motion to live on the surface of a hyperbola. For example, you could take a particle and constrain its motion to move on the Poincaré disk, or the hyperbolic 4 space, or the hyperbolic 3 space. This is a quantum system with a single degree of freedom, whose symmetries are the Euclidean CFT symmetries, times time. So the Hilbert space of this particle, the wave functions of this particle on this space on which it's moving, will transform under a few, if not all, of these representations. So for example, if you study a particle on the Poincaré disk, and you study the wave functions of this particle, you'll find two collections. You'll find a collection of wave functions that look like bound states, a discretum of bound states, and you will associate those with these discrete series. And then you'll find a collection of wave functions that oscillate infinitely towards the boundary of the Poincaré disk. And those are like a Fourier basis. Okay, they're themselves non-normalizable. However, they may span normalizable functions. And so it's sort of an interesting exercise to get intuition about the structure of the Hilbert space of a quantum theory that transforms under these non-compact symmetries. Okay, so that's a fun exercise to do, but I'll allow you to do that on your own time. Now, for S equals 0, for spin non-zero, the structure of the representations is effectively the same, except for two things that happen. First of all, in the complementary series, the range of delta is slightly reduced. To 0 to 2. And the discrete series, we can actually be a little bit more specific about. They come in a particular structure. So, and it's useful to introduce a parameter, t, ranging from 0 all the way to s minus 1. And the weights of the discrete series can be expressed for spin s as either 2 plus t or 1 minus t, which is the shadow weight, okay? And so you'll note something already, that when for the maximal depth, okay? I'm saying this now, I'm just mentioning facts, and then we'll explore so I haven't told you about discrete series yet, but then we'll explore how they manifest themselves from the point of view of linearized fields in de Sitter. But now I just want to mention this because you read this in this Dobrev book, and it's a peculiar looking fact. But so for each spin, there's a collection of different irreps in of SO4,1 in the discrete series. And when t is s minus 1, which is the maximal, the weight looks like s plus 1. Some of you may recall that this is the weight of a conserved current in a 3D CFT. Okay, and then the weight goes lower and lower. Okay, so we can call it a mathematical prediction, since these representations were discovered early on. We can call it a mathematical prediction about a particular potential collection of particles that furnish in de Sitter these unusual representations. Okay? Okay, now, yeah. So because there's a mathematical reason, and I'll give you the physics reason when we study with what happens in field theory. So yeah, let me get there. Now, everything I said, so let's pause for a second. Everything I said is all good, except I haven't talked about the quantum state yet. So I'm assuming throughout this discussion, in order to exploit maximally all of these symmetries, that there exists a state which is normalizable and annihilated by the generators of the de Sitter group, a de Sitter invariant state. Now, at least at the free level, there is little doubt that such a state exists. But I would like to mention, and for fixed backgrounds in de Sitter, even when they're interacting, there's little doubt that such a state exists. When we consider issues about gravity, the situation is murkier. But I don't want to get into that. This is the story of potential perturbative infrared effects in de Sitter. But let me mention a few words as to why this might be an issue from the perspective from a sort of intuitive physical picture. So imagine that you have a theory that interacts in de Sitter. Remember, de Sitter is an inflating piece of volume in time that grows exponentially, and you're now integrating, for example, a virtual particle over a loop, and you have to integrate this vertex throughout this infinitely expanding region of space. And even though the coupling of this loop may be small, the fact that you're integrating over such an enormous amount of space may lead to an effective growth of the coupling in the deep infrared, which means a very late time. Okay? And the loop calculations in de Sitter, because of all this discussion we've been talking about there being two operators, about the not being able to impose boundary conditions in the future, are different from those in anti-de Sitter space. And so you're allowing modes to propagate and fluctuations to occur that are more aggressive near the boundary of your space than they would be in the case of ADS, okay? And so the problem is of a qualitatively different nature, and solving one doesn't imply you've solved the other, okay? And so regardless of whether or not a de Sitter invariant wave function exists in interacting field theory and fixed de Sitter background, it remains important to understand its structure and how these effects may be regulated, resummed, or whatnot. Okay, so there's an interesting, so when we study QCD, or Yang-Mills theory, there's a growth of couplings in the infrared, which is interesting. It's not a matter of whether the theory exists or not, it's just a matter of the fact that the wave function of QCD in Yang-Mills becomes extremely interesting in the IR. So interesting, it's a very hard problem that we can't solve it. In de Sitter somehow, the situation is similar, except that we replace the IR of QCD with the very late time limit of your cosmological space. And we'd like to understand the structure, particularly in that regime, of the quantum state of de Sitter. Okay? So that's an interesting quantum field theory problem, and solving it may involve all sorts of interesting resummation techniques. Yeah? Right, so I'll get there. But not the language isn't beta function anymore, I think, because the background's time, I think the language has to change a little bit, and it has to be guided by these symmetries. It might have to do with things like anomalies in the conformal symmetries, right? Which are in a sense beta functions, but the structure of the calculation is a little different. So there's two effects. So this is the debate. This is precisely the debate. There's two competing effects due to the same physics. On the one hand, you have an exponential dilution, and you'd say that this is innocent. On the other hand, because there's no time translation invariance, you can borrow energy and produce particles. And so both of these effects are occurring due to the same dynamics, due to the same background, and the discussion is between whether the dilution at very late times wins against the particle production. And the two different possibilities are, but it's really, you're comparing, you see, it might end up being a delicate question for that reason, right? Because as we said, yes, space is expanding, but for these very light fields, for example, the profile never dilutes away at late time. And so it's not something that I would rely too heavily on intuition. It's something we need to calculate. And we'll see a manifestation of this when we look at the structure of the wave function. It may just be a technical point. But you know, I find it analogous to sorting out the soft photon theorem in QED or something. It's an important technical point, and there's physics behind its solution. Okay, I find it an interesting problem. Whenever we encounter a question in perturbative quantum field theory that we can't nail completely, we should make sure we know how to do it. Yeah. Oh, for the fermionic one, I'm not going to discuss them, but there's analog representations for half integers. You can put fermions in de Sitter as well. It's analogous. The fermions, well, let me not talk too fast. I forget whether or not the complementary series are there or not. I'm sure the principal series are there. But I forget if somehow they end I don't know, I shouldn't say, I can't remember. But the analysis is done. Okay. So, whoa, okay. So let me talk about the quantum state. And I'm going to talk about a quantum state which for the free theory exists and is de Sitter invariant, and in the literature is known, it was discovered by many people roughly at the same time, but in the literature it's known as the Bunch-Davies or the Euclidean vacuum state. And I think it will be useful to discuss this state from the perspective of the Schrödinger picture, okay? So the Schrödinger picture in quantum field theory basically asks us to consider the following object. It asks us to consider the overlap of some quantum state in the theory with an eigen state of the field operator itself at a constant time. And what that does is it produces a functional over the space of all configurations at a constant time slice, which are functions living in some function space. And we'd like to consider this object. Okay, so rest assured, even in quantum field theory, the wave function that you learned in quantum mechanics was always still there. It's just that we rarely calculated it. Okay, now the reason it might be useful to consider the Schrödinger wave function in the context of de Sitter is what I said before, that it's not clear that the natural observable is an S matrix, but rather it might be the physics of fluctuations on a constant time slice throughout space. And so a natural object to consider is a functional over the fields over all this spatial slice. Okay, so it seems to be, though we're not accustomed to studying the Schrodinger wave function in quantum field, de Sitter might suggest it's a useful thing to calculate. And indeed, it's a nice thing to calculate, and its structure respects the symmetries in an interesting way. So let me discuss, yeah.
Why would you consider the Fock space analog of two sets of commutation equations? The latter one is easily understood.
Yes. So what you would have to do in that case is take complex linear combinations of these two Hermitian operators and try to find a vacuum annihilated by this type of combination. That's what one may do. In fact, what one actually does is a little more, less intuitive. One considers the behavior of the field in the region eta going to infinity, identifies in this region where the momentum of the mode is far larger than the de Sitter scale, identifies the vacuum of Minkowski space in that effectively Minkowski region, for those large K modes, discovers the analog of A, which annihilates the Minkowski vacuum, and assumes analytically that for all K, that this is defined to be the vacuum everywhere. Now, this is a perfectly reasonable definition of a quantum state, and in fact, it's the path integral I'm going to write down in a second. The reason I'm going to write it down in the path integral language is that the structure of the wave function will look familiar and interesting. Yeah. So there's no problem with doing a Fock analysis. All perturbative field theory at that level is fine. So let me now describe in a path integral language what I just described in terms of the Fock space. Yeah. Oh, over here? Oh, did I? Thank you, Logan. It's either psi or psi star. So I'm taking the overlap of a quantum state in a complete basis of field operator eigenstates. Oh, sorry. This is what's worrying you? Oh, thank you, Loga. Okay. It's good to be careful. Thank you. Okay. So what I'm going to calculate then is a function of the functional, which means a function over the space of functions at some constant time slice. And I'm going to define it to be the following path integral, which will be a path integral over all, well, let's label the time where we measure things to be eta c. So we're going to take an integral over all field configurations over space and time. However, we're going to impose an unusual boundary condition, which is that the fields will vanish in the infinite Euclidean past. Now, in order to get some intuition about this boundary condition, the boundary condition on the other is just the profile, the squiggly phi. So phi at eta c is just the real profile squiggly phi. That's the measurement of the configuration. So let me give you another homework problem to get familiar with this. I would invite you to calculate in the path integral language, to remind yourself of the calculation of the ground state of the quantum harmonic oscillator in the path integral language. And you will end up with an expression that's rather similar, except, of course, the overlap is between a position x and a quantum state. But still, we have now a path integral over all paths x of t, and our boundary condition is that the infinite Euclidean past, our x of t vanishes. E to the minus, because this is a path integral. It's a standard path integral. The ground state wave function is given by the Euclidean path integral, or it's given by the standard path integral with complex boundary with complex field configurations. So remember, wave functions have phases as well. And so when we do it in this way, we're going to acquire an object with a phase and a real part. And the phase will be due to the real piece of the solution, and the real part will be due to the imaginary part of the solution. So in order to, the best way to understand this is to do the exercise I suggested. Because even a harmonic oscillator, in principle, there's a phase e to the I e t. If I give you a strictly Euclidean definition, you will have essentially considered the problem at t equals 0. You've killed the phase. So this is a slightly more Lorentzian way of calculating the same object, and one can prove that this thing solves the Schrödinger wave function of your theory upon variations of the boundary data while fixing the Euclidean past to be the same. There's an I, because we're going to the Euclidean past. So what that means in the language that you might remember from your course is that, remember when you when you took an overlap in quantum mechanics and you inserted a complete basis of energy eigenstates and you summed over them and you wanted to isolate the contribution of the ground state, one trick that we learned was that because we had e to the I e t, was to take e to be slightly imaginary and then push it down so that the lowest of the energies is the only one that contributes. That's what I'm doing here. Now, conceptually, it's different because, as we keep on mentioning, there's no time translation invariance in de Sitter, and so there's no discrete spectrum of energy eigenstates. However, it is an interesting state in the Hilbert space, as we will explore, and it has the virtue of producing fluctuations which agree with the Gaussian fluctuations of the CMB. And so it's an interesting state to consider. Okay? So now, for example, if we were condensed matter physicists, we wouldn't just be interested in an S matrix, we might be interested in the structure of the quantum state itself. And so we look for interesting quantum states in our system. So I claim that this is an interesting quantum state in the field theory in quantum field theory in a fixed de Sitter background. Yeah. So it's the one that the modes are e to the, are you worried about the sign? No, this one is, so this one is imposed at some eta equal eta c. Yeah, so that's like taking the overlap with the position operator at some time t with the state in the infinite Euclidean path. So one has to complexify the field configuration. Infinity. So the contour is you end with a real value at eta c, and then you go to the. Oh, sorry. What? You can take eta to be any complex contour that ends on a real value, and goes all the way to the past Euclidean infinity.
Usually I get a certain wave function.
You get a wave function.
Now you want to evolve it in Lorentzian fashion.
That will give you the additional phase.
That's what you're talking about.
Yeah. So you see, had you done it purely on the imaginary axis, you would have had no phase, and it would have been like studying the e to the minus x squared without the plus I e t. So that phase, if you do it in the Euclidean way, you can. What's that? At the perturbative level, I believe so. You're worried about the possibility of poles and things like that? Yeah. So I suspect at the perturbative level it's okay. But this is a question about, perturbation theory and how to... all of these questions are already relevant at the level of the harmonic oscillator that we discussed. There's no difference. Yeah. The only singular structure is at eta equal going to 0. That's where the pole of the metric is. But we're ending this before there. Eta is some small negative number that's less than 0. So we've evolved to some late, but not infinite time. Okay? Well, it has to do with, you're worried about the sign now. Yeah, so the sign, it has to do with I forget now what my conventions were, whether eta was going from minus infinity to 0 or infinity to 0. Okay, let's leave the sign as a homework problem, because one of them defines psi star and the other one defines psi. And I don't, I just, off the top of my head, I'm not going to get the sign right. No, they go like e to the I omega eta, because eta is a negative. They go like e to the minus I omega eta. No, because it's forward pointing. It's forward pointing. So it's e to the minus. So maybe it's plus I omega. I've confused myself now. E to the minus I omega t.
Minus I omega t minus t initial.
Yeah.
And then you take the t initial to plus I infinity. So that the initial.
Yeah. Right. I think it's a contour. Okay. Let me. Okay. This is a question we can answer. This is a simple question. This would be, right, so you're worried that whether there are going to be singularities as we analytically continue and we complexify the space of functions.
Yeah, I mean, if you specify the contour, you need to be clear what contour you're doing. Now you're saying you can take any contour that goes to.
Well, any contour that doesn't cross a singularity. Any.
The contour to go up or to go, yeah.
No. It has to go down, and it has to be a contour that's close enough. So there does exist in perturbation theory a contour that doesn't have singularities, and then you don't want to push it too far. Okay. This is a question about field theory in general, because the vacuum state of a quantum field theory can be defined precisely in this way. So I didn't want this to become a discussion about the contour. This was supposed to be the straightforward part. But let me say a few, because we're running out of time. Let me say a few things about the structure of the wave function when you actually calculate it, okay? So, okay. So the wave function at late times acquires, again, for delta real, let's talk about the case delta real now, just for the sake of specificity. The wave function acquires the following structure. There exists a piece which is local and diverges at late times, which is a pure phase. Okay? So there's a piece of the wave function that at late enough times is local and diverges. And then there exists a piece which is non-local. And takes the following form. I'm absorbing factors of eta c. Okay, I kept them in the phase to emphasize that upon canonical normalization of the field, the phase diverges. But there's a piece that's non-local in the field that captures correlations of the field at separate points. And the kernel of this non-local piece takes a familiar form. It takes the form of a two-point function in a conformal field theory. And if we add a cubic interaction at tree level, we can continue this process. and find a function of 3 points, okay, which was constrained, and the constraints of the symmetry as discovered by Polyakov are enough to fix the form of this 3-point function completely. So this takes the form of a 3-point function in a Euclidean conformal field theory. And at tree level, this structure will continue. Will continue. Let me take a few minutes to just finish the statement. Will continue onwards. Okay. Now we can also consider this wave function in momentum space, and it's a useful thing to do to check that this is indeed in all directions a Gaussian suppressed a piece of the wave function. And in momentum space, it looks like as follows. So there's a -2 delta, what is it? +3? What's the Fourier transform? We have 3x, sorry? 3 minus 2 delta. Eh? Okay, it takes the momentum, the Fourier transform of the momentum. The important thing, it's a positive function of k. Okay? And so we've produced a wave function whose Gaussian fluctuations are suppressed in all possible directions. So, in the case where delta is approximately 0 or close to 0, rather 3. So for the massless field, these fluctuations, no, it's 2 delta minus 3. Yeah, okay, good. So these fluctuations take an important form. They go like k cubed integral d3k phi squared. And in fact, these are the fluctuations of the inflaton. So when people say in inflation that we have a Gaussian and scale invariant spectrum, from the perspective of the wave function, what that means is that the wave function is dominated by a Gaussian piece, and that the power spectrum, that the kernel that hits this Gaussian piece is a power law in momentum. And specifically, for the case of inflation, the power of the momentum is close to 3. Now, another thing I'd like to observe about this wave function, specifically in the massless limit, which is the... Yes, here I'm setting delta equal to 3. This is how I remembered that it had to be 2 delta minus 3. So I'd like to... give now another discussion about masslessness in de Sitter and why it's more infrared. The infrared is stronger. So what would the wave function of a massless particle in 4-dimensional flat space look like in momentum space? It will be Gaussian suppressed, right? And it'll go like in e to the minus integral d3k times k, phi minus k, which at low k, if I calculate the 2-point function, for example, will go like 1 over k. That's an infrared, still okay in the infrared when k goes to 0, because generally you integrate against d3k. In the case of a massless field in de Sitter, the propagator of the particle, so the expectation value of 2 momentum modes of a massless field, so integral psi squared phi k phi minus k, will have a 1 over k cubed. In the IR, this is quite stronger. For example, the Fourier transform so for delta equal 3, or for the massless case, we have a 1 over k cubed, And if we take the Fourier transform of this object, we get a logarithm of the distance between the two insertions. This grows with distance. There's no cluster decomposition. The correlation doesn't decay at very large distances. It grows logarithmically. So this is an important phenomenon because it's telling us that already at the free level, the infrared structure of our quantum state can behave rather differently. And if we calculate the wave function for anti-de Sitter space, for example, this will not be a phenomenon we observe. Okay? So to go back to Suvrat's question about how can we gauge whether or not the infrared is stronger, well, what happens at the level of the quantum state is that when you now turn on interactions, which will have some couplings, and you want to sort of calculate loops, you have to propagate something which at one point, at some region of space, will be like integrating d3k over k cubed. So you're propagating particles that are sensitive to the infrared in a non-trivial way. Okay? And so there lies the interest of the problem from a perturbative type of picture. So light particles in de Sitter are something to think about. And for gravity, which I wanted to get to, but there's not enough time now, but the linearized fluctuations of gravity, remember there was this 1 over eta cubed term as well, have a very similar structure in their wave function. Photons don't, but gravitons have a similar structure. And so it's this sort of balance between preserving the conformal symmetry, which means that the infrared affects some, maybe they slightly renormalize the weights, whether the resummation produces a shift in the canonical data of the conformal structure, or whether they produce problematic symmetry breaking anomalies. And this, yeah. This is a long discussion. My perspective on the story is summarized in this paper over here, a paper with Dan Friedman, Tarek Anous, George Kastandinidis, where we studied the question of perturbation theory in de Sitter from the perspective of the Schrödinger wave function. So oftentimes this problem is analyzed in the Schwinger-Keldysh or in informalism, but I didn't want to commit to any particular observables. So we decided it might be a good idea to analyze the structure of the loop corrections at the level of the Schrödinger wave function itself. And another reason is that, as you see clearly, the structure of the conformal symmetries is very manifest at the level of the wave function. It looks effectively as if it was a generating function of conformally invariant correlation functions at tree level. Okay? An observation made in this paper over here. So we wanted to exploit that structure and see whether we could say anything about the resummation, because from the point of view of the wave function, if you add loop corrections to the wave function in the Schrödinger picture, you might try to interpret them as some small shifts in the canonical CFD data. Okay? So this was my take on the problem, and I think there were hints that there was a natural resummation that could be done. But as far as I know, this problem it still needs a lot of work. And this is for fixed field theory in field theory in a fixed de Sitter background. When we get to the other problem, which unfortunately I wanted to introduce the concept of the wave function semi-classically for geometry, but we'll do that tomorrow. We have to confront all sorts of other questions. But anyway, so let's end here. Yeah. In the action?
I'm saying the integral has some Lagrangian.
Sorry, over here?
Yes.
So we're evaluating, right, so the path integral evaluates, so you weighted by the action over all space and for fields over all space and time, you evaluate the action finally at a constant time configuration, and the wave functions at that time a function only of the spatial configuration. This is like asking, why is the wave function at a constant time of the harmonic oscillator purely a function of x? What? The other way, from this picture over here, it's, you know, you have a quantum state psi. You take an overlap with an eigenstate of the field operator, and you get a function of phi of x. Now, this could be a non-local function, interestingly so, and it is, right? So we feed it phi of x, but in order to extract a probability, we have to do interesting things to phi of x, but it's just a function of var phi of x. Yeah. Pardon me? At tree level, and presumably at loop level as well. So long as you preserve, it's equivalent to the question of whether or not you spontaneously break the de Sitter symmetries. At tree level.
No, I don't know. I mean, there has to be an expression for the wave function. You can always expand it.
Why can you expand the wave function? The question is whether, such an object solves the Schrodinger wave equation. So this is this is a function of eta. Okay, so of course if it's normalizable, it lives in the Hilbert space. The question is whether it's produced by this path integral, right? So of course any function that's square normalizable, any function of phi of x is a wave function. What's interesting, and I can always write such a thing, assuming it's normalizable. What's interesting about such a thing, in a sense, is that we've connected it to a process that we believe is sort of a quantum evolution of a field from. Well, you see, it's an important thing because this definition applies for all times. And so here we know that such an object solves the Schrodinger equation for all times. Whereas this is just a functional that may evolve 1 millisecond afterwards into something completely bizarre. So I think it's important that this functional is connected to this definition. In other words, this lives in the Hilbert space of quantum field theory and de Sitter, but what makes it somewhat an interesting member of that Hilbert space is how it behaves under time, that it behaves smoothly under time evolution. That was in the late time. Oh, sorry, this is the late time, excuse me. Yeah. In my mind, I'm always working in the late time limit, but of course this is. Yeah. I think at tree level, it's just true. The issue that's a little trickier is the normalizability issue, but that, again, if the corrections are perturbatively small, the Gaussian piece determines the normalizability and the other terms just follow suit. And I think it's true at loop level as well. It's just a matter of sorting out why it's true. For the light fields. For delta real, this boundary condition over here, if you take, it's a little awkward. So what you have to do is you have to take eta to IZ, and then your metric becomes an ADS metric with minus, 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 minus signature. And to get it into a standard ADS, you have to take L to IL. And this is what was observed in this paper of Malacena over here. Now, one should do that with care, because when taking L to IL, you're changing a parameter of the theory. You're not just complexifying your field, you're also sort of changing your theory. And that's fine, it works out perfectly. And so indeed, that's why I say confidently that at tree level, I don't see any subtlety, so long as delta is real. Maybe it's true at loops as well. But you see, the issue is that once you've calculated your wave function, then you have to sort of see whether the integral of psi squared also produces infrared finite things as well. So it's a two-part question. Right? First, it's sorting out the perturbation theory of the wave function, and then, because even here, this looks more innocent as a wave function than it does as a physical correlation function. On the one hand, we had e to the k cubed. On the other hand, it produces log x minus y, which requires an infrared scale to make sense. So it's just a matter of sorting out those things. Now, in the case of gravity, that analytic continuation might be more tricky, right? Because generally speaking, going to doing things in Euclidean gravity, there are objects that diverge. You have to complexify the Weyl mode, and so you have to be far more cautious in that case about these statements. And so I tend to try to stick to the Lorentzian structure of the calculation. Yeah. But as I said before, my issue isn't whether I don't think the situation. I do think there exists a normalizable state that's the de Sitter invariant. In fact, I think there are many, because from the group theoretic point of view, we're allowed to have shadow operators as well. And if I take de Sitter invariant wave function that's acted non-trivially with these operators, I have an alpha of delta and an alpha of 3 minus delta. And if I integrate that sort of composite type operator over space, I get something that's actually marginal, at least in the tree-level limit. And so I can act non-trivially with all sorts of de Sitter invariant objects. And in fact, there's a plethora of de Sitter invariant states. One particularly well-known example are something called the alpha vacua, which are already a continuous collection of de Sitter invariant states which have some unusual features. So I think, in fact, there's many de Sitter invariant vacua. However, of all of them, you'd like to select some that have sort of a relatively simple looking past if you want to make connection with a semi-classical picture of how this state was produced, right? Because if not, I could just say, well, take any conformally invariant functional at some time. There you go. But that's not somehow good enough to declare, oh, this is an interesting quantum state in cosmology, because we'd like to connect that to a picture of some evolution. Yeah. Now, for complex delta, this analytic continuation doesn't work anymore. There, you really need to calculate it, and probably maybe instead of a wave function, if you want really a functional of the object that transforms conformally, a more natural thing to calculate is a coherent state type thing, where you have a function of z. So that so that analysis does differ, and there we can no longer rely on simple analytic continuations. Okay, so there's all sorts of. Again, it's a rich problem. It's not a problem that has a one-line answer. You have to analyze different cases and see how the different representations connect and see if there's special points. For example, one thing we can already say here, imagine, sorry, I know I'm taking too much time, but let me just make one more comment because I like this problem. So imagine we quantized in global de Sitter. Where our mode naturally splits into the spherical harmonics on the sphere, right? So we have configurations on the sphere, and we have spherical harmonics, and our function is a function of the Fourier modes on the sphere. One of these modes, for the massless case, is a zero mode. This mode is simply non-normalizable and must be removed from the spectrum, okay? And in the interacting case, the fact that you have this non-normalizability in the free theory, if you add a lambda phi to the fourth, means that at least pieces of the theory that connect to that zero mode are intrinsically strongly coupled. Because there's no Gaussian suppression for the zero mode of the particle in the free sphere. Okay? And so there's all sort of, there's all sorts of infrared physics that one has to sort out. Yeah. Anyway, I could go on indefinitely, but I shouldn't. Thank you.